In the previous lecture, we learned about this sequence called the Fibonacci sequence, and there's still more to be said about that, so let's get started. To begin, let me remind you of how it's defined. It's defined using the formulas that you'll see on the left right here. First of all, the first two terms are 1 and 1. That is to say, f1, the first Fibonacci number, is 1, and f2, the second Fibonacci number, is also 1. After that, the recursive formula takes over. So fn is defined to be fn minus 2 plus fn minus 1, which is really just the mathematician's fancy way of saying to get the remaining terms in this sequence, you just always add the previous two terms. So for example, f3 is f1 plus f2, that will give you 2. f4 is f2 plus f3, which gives you 3, and so on. Once you get the hang of it, you could do this rather fast, just writing them in a line. You write the 1 and the 1 to begin with, and then add them and get 2. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Now, we encountered this sequence in a little problem having to do with trains, but Fibonacci was an Italian who lived many centuries ago, and he didn't know anything about trains. So how did he explain this sequence? Well, I'm going to tell you the answer with a little bit of a fib, and at the end I'll explain the fib. But this basically is what he said to do. Imagine you have a simple creature that reproduces just by splitting. But to make it interesting, let's say that when it splits into a big part and a little part. Let's also assume that this always takes one day to do this. So if on a certain day you have a big creature, and then you come back the next day, what you'll have is a big creature and a little creature, as I've indicated in the diagram on the right. A big creature on one day leads to a big creature together with a little creature on the next day. Now, what about the little creatures? Well, the little creature isn't big enough to split. What it's big enough to do is just to grow up, right? So the other rule says if you have a little creature on a certain day, then when you come back the next day, it will have turned into a big one. Okay, and that's it. Those are the two rules. In one day, a big creature turns into a big one and a little creature simply turns into a big one. Now, what we'd like to analyze is what's going to happen if we start this process out on day 1 with one big creature. So this is indicating day 1 over here where I'm circling, okay? And then this will be what we have on day 2, right? We have a big one and a little one. And then on day 3, the big one will have split into a big one plus a little one, and the little one will have grown up into a big one. So you'll see we have a total of 2 big and 1 little. That's altogether, of course, 3 creatures. Now, I'd like you to do a little exercise. After I explain the exercise, I'm going to pause. I hope you pause the video and try to work this out. And here's what I want you to do. I simply want you to work things out until day 6. I've shown you day 1, day 2, day 3, continue on to day 4, day 5, day 6. You'll need to get yourself a piece of paper and leave enough room so that you can continue that as you go to the right. Okay, try that now. Okay, I hope that you did that. And now you can check your answer against what I'm showing you here. Here I'm showing you from left to right, day 1, day 2, day 3, day 4, day 5, day 6. So for example, how did I get what I did on day 4? Well, there was a big creature shown at the top on day 3 that turned into a big one plus a little one. Then I had a little one, which turned into a big one, and then I had another big one, turned into a big one and a little one. So from top to bottom, I have B, L, B, B, L, big and little. That's a total of 3 big ones and 2 little ones. You might want to pause again. I would like you to check your answer against what you're seeing here. And now I'm showing you a table that shows what you saw in the diagram that you just made. So in the first column on the left, I'm simply recording the day from 1 through 6. And then I'm showing you for each day, as you go across a row, the number of big creatures, the number of little creatures, and then the total. For example, on day 1, there was 1 big creature, no little creatures, for a total of 1. On day 2, 1 big, 1 little, total of 2, and so on, all the way down to day 6, where you should see that there were 8 big ones, 5 little ones. That's a total of 13. Now, if you remember the numbers in the Fibonacci sequence, and those are called Fibonacci numbers, you'll see everything here seems to be a Fibonacci number, with perhaps the exception of 0, which we didn't mention before. In fact, if you look at the first column, it looks like exactly the Fibonacci sequence is beginning there. If you look at the second column, which is about the little creatures, well, it looks almost like the Fibonacci sequence, except we have this 0 up front, and you probably remember that's what happened in the train sequence. And then if you look at the last column, you'll see, again, it looks like the Fibonacci number sequence, except the first 1 is missing. And indeed, all of these will continue on in just the way you think, according to the Fibonacci sequence. You can explain, really, why this has to happen. To do that, let me just go on to day 7 and show you how I know what numbers are going to arise on day 7. Well, let me start with the number of big creatures on day 7. How do you get a big creature? Well, there's 2 ways. The previous day, there could have been a big creature that split, and that will give you still a big creature on the next day. Or you could have had a little one that grew up. And in fact, as you think about it, you realize every creature you had on the previous day gives you exactly 1 creature today. One big creature. So that means that the number 13, that was the total on day 6, must in fact be the number of big creatures on day 7. On the other hand, how do you get little creatures? Well, the only way to get a little creature is from a big creature. No, I had that correct. The only way you get a little creature is from a big creature splitting and to give you a little piece. So here we must get the number 8, which is the same as the number of big creatures on the previous day. Okay, so the 13 goes over here, the 8 goes here, and then we add them together, and that gives us the 21. And so you see, you're going to have to generate the Fibonacci sequence in all these columns. Now, I lied a little bit, and here's the lie. I didn't tell you about the sex. Sex is a little bit confusing. Fibonacci didn't know about asexual reproduction with little creatures like this, so he explained it involving rabbits. The confusion that you might have is that you have to talk about pairs, and that's what he talked about. He talked about pairs of adult rabbits producing pairs of baby rabbits. Now, this whole business about the Fibonacci numbers in biology may seem rather far-fetched to you, but I want to convince you that maybe it's not as crazy as it might sound. And to begin, let's look at this sunflower right here. Here's a photograph of a sunflower. If you've ever looked at the head of a sunflower, you've noticed this beautiful spiral pattern. You'll notice that there seem to be spirals all over the head of the sunflower. In fact, as you look at it carefully, you'll say, well, wait a minute, they really go 2 different directions. Some are spiraling one way and some are spiraling the other. And wherever a pair of spirals meet, there's a seed. What I want to ask is, how many spirals are there? Well, I took this same photograph and I began to mark it up by marking the spirals in one direction in red and the spirals in the other direction in green. I did this as carefully as I could, and then afterwards I counted how many spirals I was seeing. And here's the answer. Going one way, marked in red, there were 21, and going the other way, marked in green, are 34. And those are successive numbers in the Fibonacci sequence, 21 and 34. You'll get a similar result if you, say, pick up a pine cone. Just go out anywhere, pick up a pine cone. To see the pattern, it's probably best to look at the bottom, as we are here. And you'll notice again that the features of the pine cone, which happen to be called bracts, B-R-A-C-T-S, arrange themselves in spirals. Count the number of spirals, and you'll find Fibonacci numbers. This will also happen if you try a pineapple, which has these same spirals, or say an artichoke. And here are other examples. This is from a little chart that used to be in the textbook. I don't think it's in the present edition of the textbook, but it shows the examples I've already mentioned, plus some others, various occurrences of Fibonacci numbers in nature. And finally in this lecture, the last thing I'd like to do is I'd like to tie this up with the spirals somehow. And what I'm going to do is I'm going to take the Fibonacci sequence and create a squared off sort of spiral in a very simple-minded manner. I'm just going to start at the innermost point that you're seeing there, and I'm going to go one step to the right. Then I'm going to go one up, two to the left, three down, and so on. You'll notice I'm using numbers in the Fibonacci sequence. 1, 1, 2, 3. I go 5 to the right. I go 8 up, 13 to the left, 21 down, 34 to the right, and now I would like to go 55 units upward, since that's the next Fibonacci number, but here I run out of room to do it, so I can't go any further. Now looking at that, that looks rather like what we call a logarithmic spiral, the kind of spiral that you might see on a seashell.